send out the link to the event shortly after I get it from IEEE National. I will also be sending out a certification, a PDH form. A couple people asked for that, so if you have my email, so please send it over to me, and I will send you a PDH form so I don't spam everybody. I know a couple people asked for it. Everyone will be muted automatically, so if you want to speak, you'll have to unmute. But we will put in for now, since we have such a large number of people, we're over 250 now. Can you put questions in the chat, and then we will keep an eye on that, and at the end or at breaking points, we can start answering some of those questions. So with that, I'm going to turn it over to Alvin, who's our Chicago Section Computer Society Chair, and he can take it from there.
Thank you, Bob. Can everybody hear me?
Yes, I can hear you.
Okay, great.
Yes.
Very good. Yes, so thank you, Bob. Yes, my name is Alvin Chin. I am the chair of IEEE chapter, and together with IEEE Region 4, we're very, very pleased to welcome you this evening to our talk, which is on current status of quantum computing. So we're very, very pleased to have Chuck Eastham, who is a distinguished lecturer at the IEEE Computer Society. So welcome all, and hope that you're all well and staying healthy and safe. Next slide. Yes, so a little bit about IEEE Region 4. So IEEE Region 4 serves IEEE members in Illinois, Indiana, Iowa, Michigan, Minnesota, Nebraska, North and South Dakota, Ohio, and Wisconsin. And here's just some of the links. So IEEE Region 4 has a website, Facebook, Twitter, LinkedIn, and Instagram, and you can be able to follow these channels to find future and next Region 4 events. Next slide. And yeah, so as I said, I am the chair of IEEE Computer Society Chicago chapter. So we are the Chicago chapter of IEEE Computer Society, and we deal with meetings that deal with topics with all types of computing topics. So we've done a lot of stuff on software, on hardware, on computing, on AI, on big data, cloud computing, cybersecurity. So anything that has computers in it, we covered that in our meetings. Our vice chair is Gina Martinez. And we also have our resources too as well. So we have our website. We're on Facebook, Twitter, and LinkedIn. And if you want to become an IEEE Computer Society member, you can go to computer.org/membership/join. And next slide, please. And you're all here this evening. So our featured speaker is Chuck Eastham. I'm going to give a little intro about him. He's author of he's authored scientific papers in digital forensics, cyber warfare, and cryptography. He's also published 17 computer science patents. He has a doctorate in cybersecurity. He has master's degrees in applied computer science, in education, and in systems engineering. And he's actually completing and he's doing that in bioengineering and nanotechnology. He's also the senior member of IEEE and ACM, and he's an editor-in-chief for the American Journal of Science and Engineering, and as well as that, he's also an adjunct professor for the University of Dallas in Georgia. So quite a resume with Chuck Eastham, and so we're very, very, very pleased to have Chuck to talk to us tonight. So Chuck, the floor is yours.
Well, thank you very much. Let me start by sharing my presentation to make sure we can all see it. One moment here. There we go. Just a brief before we get started. The bio is a little dated. I have since finished the second doctorate, and that's going to sound crazy, but I'm in the final stages of a third. Yes, I'm a glutton for punishment. And it's now, someone is saying no sound. Can you hear me?
I can hear you fine.
Okay, I just saw no sound in the chat room. It's also now 32 books and 22 patents. I stay kind of busy. The purpose of tonight's presentation is pretty simple. quantum computing is quite impactful for so many industries. We're already seeing applications in things as diverse as chemistry and traffic management. However, most people, including engineers, including computer scientists, don't have a really good grasp of quantum computing. We don't understand what it can do, what it can't do, why are we not really there yet, what do we need to accomplish. So we're going to have three main goals tonight. First of all, making sure we all have a good understanding of what quantum computing is, how it will impact our world, and what are the current hot developments? What's going on right now that's exciting and changing things? Now, the problem with a presentation like this, and I do give it from time to time, is that last part gets outdated quickly. And so I updated this one as late as this week because things change that rapidly. Let's begin with what is a quantum computer?
Could you switch to sharing your other screen?
Are you not able to see the slides?
We're seeing the slides in your presenter view, not as the primary display.
Okay, let me see what I can do here about that.
Yeah, it's not, the slide is not a full screen. Yeah.
Okay, I'm going to stop sharing and try sharing again. Thank you for letting me know that before I got too far down the road. Let me try simply sharing that whole screen. Is that better or no?
Yes, that's very good. Thank you, Chuck.
Thank you.
The quantum computer, if you think about it simply, sounds trivial. We're using, instead of bits, instead of transistors and ones and zeros, we're using some quantum state. Sometimes, as we'll see later, we use the energy level of electrons. Sometimes we use photon spins. There's all kinds of things that can be used. But it's basically applying quantum mechanics and making that process information. Now, why is that so exciting? Well, the main reason is there are certain things that we will see during this discussion that can be done with quantum mechanics that just don't work the same way with traditional bits. And it's not a matter of how many bits you get. If you had trillions and trillions and trillions of bits in a processor, you still can't do some of the things a quantum computer could do. Now, I always think it's a good idea to be familiar with ideas, even if you disagree with them. So I have to bring up this particular individual. Dr. Diakonov, he's a professor of physics. He's a very serious, well-respected physicist. And the March 2019 issue of IEEE Spectrum had an article from him that basically stated we're never going to overcome the problems, at least not in the foreseeable future, that everyone in this conference tonight will die of old age long before we see a working quantum computer. Obviously, I disagree with him. Obviously, quite a few people disagree with him, particularly those people that are spending billions of dollars on trying to advance quantum computing. They disagree. But the man is not a crackpot, so it's worthwhile to at least consider his opinion and not just jump on the bandwagon with everyone else saying quantum computing is around the corner, going to be here tomorrow and solve everything. I also disagree with that statement. I don't think it's going to be here tomorrow, and I don't think it's going to solve everything, but it will solve some really interesting things. And in fact, most experts, if you took a survey and took the mean estimate, it would be somewhere in the next 5 to 8 years. IBM CEO is claiming 5 years from a practical quantum computer. Now, some of you are thinking there's something wrong with this presentation right now, because doesn't D-Wave, Google, IBM, and several others have a working quantum computer right now today? The answer to that is sort of, and we'll see that in detail a little later. The whole concept of quantum computing began with Richard Feynman. He never actually did any work on quantum computing. He simply posited that we should be able to do computing based on quantum mechanics. Now, given the sheer stature of Feynman, his mere speculation drove others to actually deep dive into the topic and bring us to where we are today. And that brings up a slight side note here that I'd like to share. Unfortunately, with COVID-19, we're not doing things in person. But this, I think, is one of the values of going to conferences, IEEE conferences in particular, when they do come back in person, because you interact with colleagues and you just never know when you're going to hear an idea that spurs you on to the next great thing. Who knows? Maybe spurs you on to the next Nobel Prize winning idea. But without interaction with colleagues, we're in a vacuum. We can only come up with the ideas we come up with. And I don't know about you, but I don't come up with enough ideas on my own. I need to hear other people's input. Now, there was a major, I would call it milestone in quantum computing several years ago, wherein Peter Shor, someone is still saying there's no sound out there. And
No,
someone is,
we can hear you.
okay. Sorry about that. Just want to make sure no one's being left behind. Peter Shor developed what's known as Shor's algorithm, and it's conceptually simple. The idea is factoring an integer in polynomial time, and the actual time is log of n.
We lost your slides, Chuck.
Well, I noticed something happen on the presentation side, and then everything went away.
Yep.
Are we back?
Yes.
Thank you. Peter Shor developed Shor's algorithm, and it basically allowed us to factor integers. Now, this was the beginning of real excitement about quantum computing for a simple reason. RSA, which is still probably the most widely used asymmetric algorithm, although there are many elliptic curve variations and things like that, RSA is still widely used with TLS and with VPNs. It's all dependent, RSA is, on the fact that it's quite difficult to factor a large integer into its prime factors. And by difficult, I mean you're simply not going to do it in a practical time. By the time you have it done, it won't matter anymore. And I think someone out there needs to think themselves. In any case,
I'm going to mute everybody, Chuck, and then you have to unmute yourself.
Okay. Well, so far I'm not muted, so I'll just continue. What Shor's algorithm basically told us in simple terms is that once we have a fully functional quantum computer, RSA is no longer secure. If you did any sort of e-commerce recently, ordered something from Amazon, ordered food from Grubhub or DoorDash or what have you, there's a very good chance that process used RSA. And even more serious than that, there are secure communications going between government entities and military groups. If RSA were broken today, then basically much of modern online banking, e-commerce, and even secure communication would be dead. So this, when he showed basically that a quantum computer could factor large integers much faster than a classical computer ever could, that suddenly got everyone very excited about quantum computing and its impact. And we're going to see a lot of that in just a little while. Grover's algorithm was another important algorithm. It's a search algorithm, and it's been proven mathematically to be simply one of the better algorithms for searching. I'm sorry, I keep getting pop-ups from people requesting things. It's a very effective search algorithm. Now, everything in quantum computers comes back to the wave function, which means Schrodinger's equation. And you can see one version of Schrodinger's equation on the screen. Now, one of my complaints about quantum education is that, yes, if you're going to do quantum computing research, this needs to be second nature to you. You need to understand it, be able to discuss it in detail. But you don't need that level of knowledge in order to be able to simply understand what quantum computing means, to be able to understand the impact of quantum computing. And until recently, most books on quantum computing were written assuming you had a robust mathematical and physics background. There are several out there right now that are meant for the person who doesn't have that. Quantum Computing for Everyone is one such example, and Dancing with Qubits is another. They're both made for that person who might be a computer programmer or an engineer in some other area who would like to understand quantum computing. Just be aware that those sorts of books will not put you in a position to do research in quantum computing, just to understand the news that you're reading about. There are really two main branches we're talking about. One is the actual doing computational work with a quantum computer, and the other is quantum key distribution. Now, quantum key distribution is moving much faster. It's much further ahead, and we're going to see a lot of exciting things have already happened with that, and it seems like every month some new announcement in that area. Now, there are lots of different quantum key distribution protocols. Not all of them are based on quantum entanglement, but some are. And essentially what you do with those that are is you entangle some particles, and then by manipulating the bit on one end, you instantaneously manipulate the bit on the other. Now, I find it hard to believe that most of you in here probably aren't at least somewhat familiar with quantum physics and things of that nature, thus your interest in this talk and the fact that you're IEEE members. But in case you're not, let's briefly talk about what we mean by quantum entanglement. Essentially, two particles wind up having a shared wave function. And what that means in practical terms is if I can take those two particles and I can separate them by any distance whatsoever, when I have a force affect particle A, particle B changes instantaneously to match. Now I said instantaneously, and someone is out there thinking right now that can't be. Nothing can accelerate past the speed of light. It can't be instantaneous. Well, as far as we know, this does happen instantaneously. Einstein called it spooky action at a distance, and he went to his grave thinking there was some mistake. Frankly, if you want me to explain to you how quantum entanglement works or why it works, I can't. If I could, I would be in Stockholm picking up my Nobel Prize, and, well, this isn't Stockholm. No one knows why. But countless experiments show it works, and that's one of the most bizarre things about quantum physics in general. There are many, many topics that we know for a fact it works. Literally thousands of experiments have validated, but nobody knows quite why. We know this is what happens, we don't know why. So just a little food for thought as you dive into quantum computing more deeply. There's only so much we can cover in one talk, but as you dive more deeply, don't be surprised if you find topics that you struggle with, that you find yourself walking around wondering, I still don't get that. Trust me, some of those things nobody gets. If you got them, please give me a call and let me know what you found out. I'd like to hear your explanation. Now, there are 4 companies that are actually already offering quantum key distribution products. That's an indicator of how far advanced this is. We can already do it, and we can do it practically. The main reason we do it is to exchange a secure key. In other words, you and I would like to communicate, and we'd like to exchange a key. Right now, there are so many algorithms out there. Diffie-Hellman's the oldest key exchange. MQV would be my preference because it has authentication built in, or elliptic curve MQV, but none of those have 100% security. Why does quantum key distribution have 100% security? Because nobody knows why it works. I have bits here and I have bits here. I apply a force here, it automatically changes these here, and those bits could represent the bits in a key. Since we don't know the process of them being entangled, we don't know what communication is occurring, it is literally impossible to tap into it. It's also instantaneous. So this poses a really good option for highly secure communications. Basically, we want Alice and Bob to agree on a private key, even assuming an eavesdropper. Now, I just mentioned not all the protocols use quantum key entanglement. Those that do are completely secure. You couldn't eavesdrop if you wanted. Those that don't simply have a process whereby you will detect if someone eavesdrops. Why is that? We have some details coming up on the slide, but the short answer is this. One of the oddities of quantum mechanics is as soon as you interact with a particle in any fashion, including measuring it, you've just changed it. So if I'm exchanging bits with someone else via quantum key distribution, the very act of someone intercepting it and reading them will change them, and we will know someone intercepted. It's impossible to interact without that happening. So the BB84 protocol is one of the oldest and most widely known. They basically have a stream of photons randomly polarized in one of 4 polarizations you see on the screen. Bob, with our traditional Alice and Bob, measure the photons in random orientations. And Bob tells Alice in the open what orientations he used, but not what bit values he got. Alice sends Bob in the open a list of positions at which those orientations are correct. Alice then selects some random subset of the shared bits and reveals them to Bob in the open, and that's the really cool thing. All this is happening in the open. If Bob notices any issues, any differences, that means someone, we traditionally call that Eve the eavesdropper, has intercepted and has changed the bits by reading them. This means that we can exchange a key over an open channel, and no, in BB84, we're not stopping someone from intercepting it, but we'll know when they do. And just as a side note, I have a saying I always do when I'm teaching or talking. It is no extra charge for extra knowledge. For those of you who don't know, Alice and Bob come from the original RSA paper published in 1977. They used Alice and Bob as an illustration of the two parties in encryption. And since then, I think every cryptography book or paper ever written uses Alice and Bob. It's an unwritten rule. They don't tell you, but everyone does it. Now, in the real world, what's happening? 2014, that's 7 years ago, China began installing a 2,000-kilometer quantum communication link. 2016, they launched a quantum science satellite, and they're testing quantum entanglement. 2020, a CubeSat named SPOO-QI Spooky 1 was used to produce pairs of entangled photons. If you're not familiar with satellite technology, CubeSats are relatively small and expensive. I've seen a lot of aeronautical engineering students work on them, and some even get them launched into space. They're that affordable. You don't have to have a multi-million-dollar grant, a few $1,000s, and you're in the CubeSat business. Tokyo quantum key distribution is a network, and it uses all sorts of different technology, but the quantum part is responsible for the key exchange so that they can have a secure video link, and they actually demonstrated it with a secure TV conference over a distance of 28 kilometers. And I show you that on a Google map and how far it would be to drive. That seems like a long drive for that short a distance, but Tokyo is notoriously crowded and driving is slow. 2017, China announced a 2,000-kilometer quantum fiber link connection between Beijing and Shanghai. And you can see the distance here on a Google map. And you notice I'm going progressively longer. Now, I'm not going to read every item on this timeline. You can read yourself, and I believe they're distributing these slides in PDF format. But I want you to see some highlights. Quantum computing has come so far so fast. In 2006, the first 12-qubit quantum computer was benchmarked. And we've gone past that in just 14 years quite a bit. 2009, National Institute of Standards demonstrates multiple computing operations on a qubit. In other words, not just making the qubit, but make it do something. Make it do something practical. 2012, and this is going to get us to our big problem, decoherence was suppressed for 2 seconds at room temperature. Decoherence is a problem we'll get into more detail in just a moment, but it's the single biggest problem facing quantum computing, and most attempts to suppress decoherence do so by supercooling, which is problematic in and of itself. Keeping room temperature decoherence suppressed for 2 seconds was quite a breakthrough. Now, one reason why you're not seeing a quantum computer at your local Best Buy right now is decoherence. 2 seconds isn't very long. It's a fantastic result for a physicist or a research engineer, but if you're trying to set up a data store and write a program for it, 2 seconds really isn't effective. Until we can overcome that, you're not going to see those quantum computers in practical use. Although I will correct myself quickly, I have no doubt you will soon see at Best Buy something labeled quantum computer. It won't actually have any quantum in it, they just say that. I recently purchased a TV where the salesman tried to convince me it had nanotechnology, and we had a really vigorous argument on it until my son drugged me out of the store. 2017, IBM reveals a working 50-qubit quantum computer that can maintain its state for 90 microseconds. I think you're beginning to see the problem. It's not the qubits, it's how long can they stay coherent. 2018, U.S. House of Representatives passes the National Quantum Initiative Act, $1.75 billion for quantum computing. It's a small amount in the world of quantum computing, and I'm going to head off a question that I always get asked at the end of these sorts of talks. Who in the world is most ahead on quantum computing right now? China. And I base that on several things, not the least of which is I'm a reviewer for some of the IEEE journals, and I get a lot of quantum papers to review, and it seems like there's constant stream of really good papers from Chinese universities, and they're constantly pushing the envelope, not to mention they have a lot more money going into it. Now, 2018, D-Wave launches the free quantum computing cloud. You can sign up for it. You can experiment all you like. 2019, IBM now has a commercial quantum computer, 20 qubit system, self-contained. As far as the price, it's one of those things, if you have to ask, you can't afford it. IBM has their open source quantum algorithm kit, QuizKit. What do we need? These are rough estimates. Many people say 100 qubits just to do a basic quantum chemistry simulation, 1,000 for effective machine learning, and 4,000 to factor 2048-bit RSA. That's not entirely exact. That's a very rough estimate. For example, some researchers at Google and the Swedish Royal Institute of Technology demonstrated, they proved mathematically, they obviously didn't have this machine, that 20 million qubits could crack RSA 248-bit in 8 hours. The bottom line is we're now talking about 50 and 60 qubit machines, and those are considered innovative, stretching the envelope. We need much more than that. Even if all of these could overcome the decoherence, we would still have a problem. We also have an issue that we have logical qubits and physical qubits. There's no specific correlation of how many it takes, but for example, Shor's error correction algorithm uses 9 physical qubits to make 1 logical qubit. So when you see a 52 qubit machine, that's 52 physical qubits, that's a handful of logical qubits. Here are some things. I love to give these slides out because of these links. You can go online and find quantum computing simulators. Some are quite trivial, but if you're very new to it, they'll help you. Others are quite advanced. Microsoft's Q# programming language basically simulates quantum behavior, including entanglement, and you can do Grover's algorithm and Shor's algorithm in it. D-Wave allows you to actually work with their cloud-based quantum computer, as does IBM. You basically, it's like in the old days of mainframes, which probably a few of you can remember, but many of you can't. You'd put together a job, upload your job, and whenever they had the next available slot, they executed your job and sent you back the result. That's how IBM and D-Wave work. So it seems like a step back a few decades. I'm not a huge proponent of one particular vendor over another. The only reason I tend to recommend beginners look at Q# is because it adds right into Visual Studio. It's free, and they have a truckload of videos on YouTube to walk you through everything and complete source code. So if you're new to quantum computing, that's a really great place to start. IBM is trying to commercialize this. They're working on a 58 qubit machine specifically for AI. University of Chicago now has a quantum exchange for research. Professors everywhere are getting involved. But we touched on this earlier. Let's go into more depth. Decoherence. Problem is, quantum particles, which are all your particles, photons, electrons, whatever, lose their state very quickly through almost any interaction. Interaction with the external world, interaction with other items in the computer. In fact, it's been shown that cosmic rays can cause decoherence. Now, the only way to totally stop quantum decoherence would be to completely isolate the system. But that's really not possible. We're talking about a quantum level. I just said that cosmic rays can cause decoherence, and it's not clear how one would even go about isolating from cosmic rays. Theoretically, if it were totally isolated, you could maintain coherence forever. But cosmic rays, background environmental radiation, all sorts of things can contribute to decoherence. The system itself can be an issue. Those quantum gates are constructed of atoms, and protocols have their own quantum properties. This is why many systems can only maintain coherence for a matter of microseconds to a few seconds. So when you see the big news flash that says company XYZ has just crossed a new barrier in qubits, they now have, let's say, 80 qubits, that doesn't mean as much because we still have the decoherence issue. Now, the most common method to combat decoherence is supercooling to a fraction of 1 Kelvin. Now, if you don't recall your basic physics and chemistry, 0 Kelvin is zero heat energy. It's the equivalent to 273.15 below Celsius. To give you a comparison, temperatures out in deep space are 2.7 Kelvin. Pluto plummets to 40 Kelvin, but we're talking about getting something down to a fraction of 1 Kelvin. So let's walk through that for just a moment. Can you just think for a moment, without getting into detailed engineering specifications, the amount of power required to cool something to that level? That's a tremendous power drain. So if I could send a quantum computer to your home today, and you were to hook up this supercooling, aside from the fact that if you don't have some separation between yourself and the supercooling, you're going to die, there is the fact that you will probably black out your entire area of several blocks simply trying to supercool for a matter of seconds. So this is another impediment. Unless we can get room temperature supercooling, you're not going to have supercooling, you're not going to have quantum computing widely used. Now, what I anticipate is at some point in the next 5 to 7 years, we'll manage to maintain coherence for at least a matter of many minutes, if not hours, but it will require large energy input, and therefore it will be the purview of major governments, large companies, or perhaps the really huge universities that have massive endowments. But most people still won't have access to a quantum computer. Now, D-Wave, you've heard a lot about their stuff, and I've got to be honest, I'm a fan of D-Wave. They give these large numbers of qubits because they're not doing true quantum computing. They're doing something called quantum annealing, which is sort of pseudo-quantum computing. And because of that, they're able to get a lot more qubit sizes and do more. Now, some people criticize them because it's not true quantum computing, and some of their press releases could make it sound like they are insinuating it is. I, on the other hand, say they're at least giving us something that is practical and usable right now. In fact, NASA has one of these D-Waves in Houston, and I only found that out when I was giving a talk just like this in Houston, and the NASA project manager was in the audience and spoke to me afterwards. I didn't know they already had one, so that was nice to learn. Quantum annealing is basically having a search space that's a superposition of all the possible candidate states, and then the system evolves to the actual solution. And they use the word annealing, they borrow it from metallurgy, which basically takes metal, superheats it really hot, and then slowly cools to room temperature, making the metal stronger. Now, this is the other thing. Let's assume we could solve all that. We had decoherence at room temperature, we had thousands of qubits. It doesn't mean that quantum computers are right for everything. They're fantastic for factoring, solving the discrete logarithm problem, great for searching databases. There are even quantum algorithms for solving linear systems of equations. Those of you in linear algebra would really like that. However, they're not good for everything. And let me give you a comparison. Right now we have supercomputers, which are fantastic when you have huge numerical calculations. Astrophysicists love supercomputers. But would I use a supercomputer to do word processing? No. I would see no advantage. I would see no improvement. I'd be wasting the effort. It's not for everything, but there are many tasks it's quite good for. So those of you out there, particularly the younger ones that were dreaming of a quantum computer so you can play online video games much faster than your opponents, that's unlikely to be happening. The major players right now, there are others, but these are the big ones that have been around for a while: IBM, Google, D-Wave, and Rigetti. And most of these are working very hard to make their technology accessible to the outside world. In fact, D-Wave has chosen Python for working with programming their qubits, which is great because most people in the computer world know Python to at least some extent. There are quantum programming languages out there. I've already mentioned a few. Quasm and OpenQuasm, Quill, Q-Sharp, Q-Language, QMASM, all of those are out there. And don't panic. Some of you are seeing the ASM and you're thinking of an assembler class you took and how difficult that was to work with. Quasm is not really assembler language like. It's actually a pretty easy to use language, and they have complete working samples on the internet, and OpenQuasm is a free tool. So you could start tonight after this talk doing some basic quantum programming. What about the qubits? Basically, A qubit, until you measure it, is a superposition of the possible states. Now that's a tough thing to get your mind around. It goes back to the Schrodinger's cat analogy that everyone knows. Is the cat alive or dead? It's not a question of we don't know if it's alive or dead. It's a question of it's both until we look. A qubit, until we measure it, is all states. So normally it's compared like this. A classical bit is a 0 or 1. A qubit is often represented on this sphere. We call it a Bloch sphere. And basically, it's all those states. Now, once you measure it, you will get a 1 or 0, period. But until you measure it, it's a superposition of all the possibilities between 0 and 1 with a probability you'll get out of 0 or 1. And that's the other thing that's very fascinating about quantum physics. And I would encourage anyone to dive into quantum physics as much as your mathematical background will allow you, because it changes your whole view of the world. At the quantum world, things are probabilistic, they're not deterministic. We can say with a probability what's going to happen. We don't know for certain anything. And everything in our world, you and me included, come down to particles that operate in quantum fashion. So everything is predicated on this probabilistic foam, for want of a better term, and that's the basis of our reality. Hopefully that gives you something to think about this evening. Now, a qubit can be represented by the spin of an electron or the polarization of a photon, a number of other things, but those are the two most common because they're easier for us to work with. A single qubit, it has a probability of being a 1 and it has a probability of being a 0 once we measure it. Once we measure it, we're going to get a 0 or 1, but that measurement, in fact, changed its value. If we measured it and it came out 0, well, it's a 0 now. And that's why those quantum entanglement and quantum key exchange algorithms work. If you measure something, you've changed it, you've set it. So you can't undo what you've done. Typically, we write them using something called Bra-Ket notation or Dirac notation. And basically, a single qubit is listed here. 0 is represented on the left, 1 on the right. For 2 qubits, we see it on the bottom, 4 possible states, and so on and so forth to 6 states, 8 states, and however many you need. Now, these are states you'll have once you measure the qubit, but until you do, it's in a superposition of possible states. So the little symbol you see here is basically telling you the quantum state of this particular particle, in this case a qubit, and it's a superposition of the probability of 0 and the probability of 1. These probabilities are usually measured by complex numbers. Now, photons are commonly used because polarization is easy to work with. They also sometimes use something called a time bin encoding, and it involves having a photon processed through an interferometer. And it takes 2 beams that are derived from splitting a single light, but they go through different distances. And basically, the shorter path designates 0 and the longer path 1. So that's one way to go about storing data in photons. Electrons and photons, two of the most obvious. Electrons, we often use spin. An upspin will designate 0 and a downspin 1. Some researchers have really been focusing not so much on the electron itself, but the medium to keep it in. For example, liquid helium. Liquid helium, because it's extremely cold and you'll maintain coherence longer. So there's lots of research going into lots of areas on these topics. Now, ions are another possible use. Trapped ion quantum computers use ions that are confined with electromagnetic fields. These have been quite popular, and the first control not quantum gate with an ion was done in 1995. There was a really nice paper that I quote frequently in Physics Today in 2017, all about quantum computing with neutral atoms. The idea of using neutral atoms was they were more stable. It's a little more difficult to make it happen, but that is an area of research that physicists are getting into. Nuclear magnetic resonance quantum computing. This is an interesting approach. It looks at the spin states of nuclei within molecules to represent the qubits. And they use nuclear magnetic resonances to probe the states. Now, this is a really interesting approach because using these spin states within molecules is simply something new. It's something we haven't done before, but this is a place where I really think interdisciplinary study is helpful. You've heard the term nuclear magnetic resonance before from the medical world, nuclear magnetic resonance imaging. Someone looked at that idea and said, look, I think I can apply that to qubits. And they would only know that because they had a broad field of knowledge. Gallium arsenide is a process used to create quantum dots. Now, quantum dot doesn't necessarily relate to quantum computer. It's nanotechnology. It is a device that's nanoscale in all 3 dimensions. You have other devices that are nanoscale in 1 or 2 dimensions. I see some people posting some really interesting things up there. I appreciate that, sharing information with each other. I glance over every now and then. The electron spin in this quantum dot is subject to a magnetic field. The field is called an Overhauser field. And this is a nuclear effect that occurs when the nuclear spin polarization of one popular nuclei is transferred to another. So this allows us to use yet another approach to storing qubits. How do we manipulate them? Okay, you stored them. How do you manipulate them? The 2 most common ways of doing it has been with lasers and with microwaves. And Penn State's been working with using them both to have a little tighter control. Obviously, we're talking about subatomic particles. The ability to manipulate them is a non-trivial problem. Addressing decoherence. Now, we already talked about making things extremely cold, but that methodology, as we already mentioned, has problems. Even for a large government facility, that energy consumption is going to be problematic. You wouldn't want a quantum computer running day after day, month after month. We've talked a little bit about the background of quantum computing in general and quantum physics, but ultimately quantum computing is going to have quantum gates, just like the computer you're using right now has traditional logic gates. So we need to have quantum gates that we can use to create quantum algorithms. Now, this is another thing that QASM does very well. They have built-in quantum gate structures, so you can use a particular quantum gate, like a Hadamard gate, without even knowing how to construct it. So it's really great for the beginner. And here are a few of the common gates. We have a Hadamard gate, we have a phase shift gate, and we have the 3 poly gates. Now, these are usually represented, as you see here, as a 2x2 matrix. Here's the good news. Those of you that thought your linear algebra class was a waste of your time, it is the cornerstone of doing anything in quantum computing. If you don't know linear algebra, you're going to have a hard time because we use linear algebra to represent the qubits, and we use it to represent the gates because it operates on the qubits. And so linear algebra is the cornerstone. Now I'll go back a slide. These are the more common ones you see all the time. These are less common. There's a Fredkin gate, which is a classical computer circuit designed to basically work as a simple universal gate, which means it can be used in multiple different ways and you can reverse operations. The quantum version is a 3-bit gate that performs a quantum control swap. Toffoli gates, named after their inventor. These gates are also called control not gates, CC not gates, and they're used in quantum computers. They apply a series of gates. Ising gates, there are actually 3 of them, and they're often called Ising coupling gates. They're named after Ernst Ising, who developed the Ising model. They use magnetic dipole moments of atomic spins. When you talk about quantum gates, there's a little bit of theory to go along with them. The Gauss-McNeil theorem. Basically, this was proposed by 2 individuals. I'm sorry, I saw a question up there. I'm going to get back to that in a second. Can you do quantum computing without quantum gates? No, you can't. Just like you can't do classical computing without classical gates. Now, that was a good question, and it makes me go off on a slight side note for a moment. Long, long ago, and forgive me for saying this, I can see some of you in video, and some of you are my age or a bit older, so you'll recall when getting a computer science degree or an electrical engineering degree meant you took assembler. I realize most people don't ever use assembler in their whole life, but by using assembler, you learned a lot about things like registers, logic gates, how things work down at the really fundamental level. Today, I'm sad to say, many computer science students have never seeing that level of a computer. There are computer science students only vaguely aware what logic gates are. Well, quantum computing takes us back to where we were with the beginnings of classical computing. Now we have to get into the weeds with things like gates. So the answer to that question is, no, you can't do quantum computing without quantum gates, but you also haven't done classical computing without classic gates. Now, this theory basically states that the circuits that consist only of gates from the Pauli group's normalizer can be perfectly simulated on a classical probabilistic computer. Now, again, I tend not to like to just read slides to you, and you're going to get these slides, but the upshot of their theory is simply this. We can simulate quantum computing on a classical computer with the right conditions. So you might wonder, if we haven't tackled decoherence yet, how do we know quantum computers can do all this? One method is simulating them. Another method is mathematically proving it. And a third method is simply working with smaller items. For example, Shor's algorithm. We don't have a quantum computer that keeps its state long enough to try a 200-digit integer. But we can try a 20-digit integer and prove that works and extrapolate from there. Here are some of the typical symbols. I'm seeing lots of interesting questions up there. We'll be addressing all those in a moment. There are symbols for all these gates, just like there are symbols for logical gates in basic electrical engineering. We give you the basic symbols here. We have and, or, and exclusive or operations, just like you do in classical computing. Not and not or operations, just as well. A simplest gate simply involves one qubit, and it's called a Hadamard gate, also called a square root of NOT gate. So we bring in a state, we put it through a Hadamard gate, we get a state. If you use two Hadamard gates in succession, you basically get a NOT gate. Now, quantum annealing we mentioned before, and this answers one of the questions that popped up. I said it's not possible to have quantum computing without quantum gates. That's true if you want true quantum computing. Quantum annealing, which is what D-Wave does not depend on quantum gates. And that's why it's kind of a pseudo-quantum computing. But keep in mind that what they're doing is not true quantum computing. Now, the big impact we already mentioned was with cryptography. A working quantum computer will make RSA, elliptic curve, Diffie-Hellman, MQV, all of those obsolete. Not to panic, the National Institute of Standards has started working on a quantum-resistant cryptography standard, and they're now in round 3. Now, I'm very pleased to announce something. I had published a paper a couple of years ago that basically, I've done 2 so far, that did an analysis of NTRU encrypt versus other algorithms, and my results said that NTRU encrypt was a better candidate than many of the others like GGH. Well, I'm thrilled to announce that 2 different variations of NTRU encrypt have moved on to round 3 of the NIST standard. That means at least I wasn't completely wrong. I wasn't totally out in left field. And if I'm being totally honest, if that had not occurred, if they'd have got eliminated in the first round, I would never mention that again. I would pretend I never said that. Now, that concludes our presentation. I'm going to quit sharing my screen for a moment. That way I can see the Q&A window, because it looks like we had a lot of questions popping up in there. So let me try to go back and start answering those.
I have a few that I copied as they were typing, so let me
oh, please.
share. I'm going to share my screen of the few that I copied off. Can you see what I have here?
Yes, I can.
Okay, so those are the ones that I copied off.
Well, the first one I think we have answered. D-Wave is not true quantum computing, but I want to be clear, I'm not slighting them in any way. They brought us a practical, almost quantum computing. And that's a pretty good improvement. I mean, until we can get the full working quantum computing, I'd like to have as close as I can get now. And as I said, D-Wave has already been used by NASA, and they actually did an experiment, I think about a year ago. I was talking to one of the D-Wave representatives. They actually managed the traffic for public transit in an entire European city using a D-Wave computer. So basically, they're doing something practical and they're doing it now. Next question was, nothing supercooling. Well, supercooling has been the only consistently effective way to overcome decoherence because it takes everything down to a lower energy state so that we don't have so much interaction. Major actors over in China, primarily they do it as a team effort. It's mostly universities, and frankly, all of their large universities, are working hard on this. How many qubits to break Bitcoin? Well, that's going to be similar to how many qubits to break RSA, depending on the Bitcoin implementation, but we're nowhere close yet. So Bitcoin isn't in danger yet. Energy requirements. We are nowhere near quantum computing powering autonomous vehicles simply because we couldn't put a quantum computer in an autonomous vehicle. But you brought up a question there that I want to delve into a little deeper that goes a little outside what you asked. Quantum computing and AI. Anytime I give a talk, I like to stick mostly to strict hardcore science, but to throw out at least one thing that's pure speculation. Here I'm going to throw out the speculation. Roger Penrose, who I've always been a fan of, and last year he got the Nobel Prize for his work on black holes. I was glad to see that. He has had a concept for a long time that is widely denounced in the neuroscience world. He claims that human consciousness is an emergent phenomenon based on quantum fluctuations in the microtubules of our neurons. Now, I want to be clear. The bulk of neuroscientists say he's wrong. But Roger Penrose is certainly no quack, and you have to at least consider what he's saying, not to mention some of the scientific objections to his claim have been overcome. We still don't know that happens to be true, but some of them have been overcome. So this is your speculative question to bake your noodle a little bit the next few days. What if he's right? What happens when we do implement AI on a quantum computer? Will it wake up? I don't know the answer to that. I don't even know if Roger Penrose is right, and I'm not totally convinced he's right, but it's something to think about. What cryptographic algorithms will survive into a quantum era? Actually, none of the ones you're probably familiar with, RSA, elliptic curve, and all that will. However, there's a host of other algorithms based on totally different math. My favorite are the lattice-based algorithms, NTRU being one, but there are multivariate algorithms and other based algorithms have based on totally different math that there is no indication quantum computing can affect in any way. People are still asking about most promising other than super cold. Super cold right now is the most promising, and there really isn't a close second. Someone's asking about Fermilab, building a multi-cell superconducting microwave cavities for quantum computers, and that the N of cells multiplicatively increases the numbers of effective qubits. What they're essentially doing there is a really neat approach. Instead of trying to get one big quantum computer that has 80, 90, 100 qubits, let's make a bunch of small ones that have 8 or 12 qubits and have them work the same way that a cluster works now. That way we only have to deal with decoherence for these small little pockets. Now, I don't know that's the right approach, but it's a really cool approach and it has promise. Someone is talking about polygates being used for qubit transformation and measurement. Since the polygate is both unitary and Hermitian, you're right. Usually polygate is done as an applied magnetic field on the state. How do you make it choose transformation over measurement? Well, it's not a question so much of choosing. When you transform it, you're also causing a measurement to occur. So they're both sort of happening. It's just which one you're interested in. So I think that's handled those questions. Do we have any others? I'm looking in the chat room here. Problems with alternating for more than one qubit. That's an area I don't know anyone's really working on. Which universities have a PhD in quantum computing? Okay. This is a delicate topic. The problem is quantum computing has become a really, really hot topic. And universities can be as bad as anyone else on jumping on a bandwagon without appropriate faculty. For that reason, I know of at least one university that has a PhD in quantum computing that's totally garbage. And in fact, if you got a PhD there, I would probably not even have a conversation with you. but I won't mention the one because I don't do slander. I would say for this, any graduate program in quantum computing, if they're not requiring a background in at least basic quantum physics, linear algebra, differential equations, they can't possibly be doing real quantum computing. They're doing a pseudo business computing, which may be what you want to do, but just be careful. The major players doing it now are usually physics departments that are branching off into quantum computing. And I'd like to see that change. I'd like to see some really good, solid computer science programs do quantum computing, but there aren't that many doing it right now. In 25 years, how many quantum computers do you think will exist? Well, there's a good and a bad thing about predicting that long out. The bad thing is it's so hard to tell anything that long out. The good news is I can say anything I want. No one will remember 25 years from now what I predicted. But I would have to guess, my best guess now, is we will at least see quantum computers in the hands of governments, major universities, major companies. I still don't think you're going to have a quantum computer in your house at that time, but you never know. There could be some major leap forward in decoherence handling that changes everything. I just don't know about it yet. Someone's asking about current research in the field. It's not focused on one area. There's a lot of work in algorithms simply because you don't have to actually have a quantum computer to do it. But if you are a physicist, there's a huge amount of work in trying to store qubits, control decoherence, things of that nature. So where the most focus is in what your skill is at. There's a whole bunch of research happening in these quantum-resistant cryptography algorithms, better search algorithms, better gate operations. So you can basically go any direction you want in the research area. What do I think of IBM QuizKit? It is actually a pretty good tool, and I should have probably I thought I had it on my list. If I didn't, I apologize. It's a good tool for you to learn with. At this point, no single tool has taken over. So I can't tell you should go with Microsoft's or Quasm or QuizKit. None of them have won the day yet. What's the first thing I would do if I had a quantum computer? I've been asked that before, and I'll tell you, probably try to simulate quantum interactions of subatomic particles. To me, that's the logical, obvious thing to do. Will quantum computing always remain 5 to 10 years away? That's a good point. I mean, and you bring up the good example of fusion energy. I remember when those two chemists published in, I think, Newsweek or Time that they had cold fusion, only to be proven wrong. You usually don't publish science in news magazines, at least not initially. I can't tell you for sure. I mentioned there is one prominent physicist and a few others that think you're right. It'll always be 5 to 10 years away. But I'm seeing so much happen in the past few years that it does appear we will overcome it. Now, someone always asks this every meeting, what is happening on the monitor behind me? I usually try to mess with people and lie and say that is Skynet launching, or, oh no, you weren't supposed to see that, now I have to kill you. Actually, it's just a funny screensaver. So, but I get that question, and oddly enough, I frequently work as an expert witness in court cases, and I left it on during a court hearing, and the judge finally interrupted and said, I've got to ask, what is that behind you on the computer? So you're not the only one. I'll save that one question for later. I'll wait till I get the other ones through. Okay, how can quantum keys be deployed? I'm obviously going to oversimplify this because there's a lot of approaches. But if you take two subatomic particles and you ram them together at high speeds like they do at CERN, they're not simply annihilating, they actually produce two different particles that are now quantumly entangled. If you can then capture them by applying some energy field and separate them, they're still entangled. That's obviously an oversimplification. There are other ways to do quantum entanglement. There are natural phenomena that lead to entangled particles. But the bottom line is once you have entangled particles, any effect done on one particle is instantaneously done on the other. So that's the essence of it. How does this happen? Why does it happen? Well, the initial entanglement is at the same location, and then they're separated. But once they're separated, they're still having a shared wave function, and affecting one affects the other. And just another speculation, since ultimately communication, the communication we're having right now is just bits. You could theoretically, if you had enough qubits entangled, communicate directly, not just use key exchange, but communicate. And since it will be instantaneous, it kind of reminds me of the subspace communication they discussed in Star Trek. Just a little food for thought there. How much decoherence time we're able to achieve depends on which method and how many qubits, but usually a matter of a couple of seconds is considered really, really outstanding. Well, an application towards antivirus. Well, if we had a fully functioning quantum computer, I would believe there would be, because we can examine multiple states at one time, which is kind of how Shor's algorithm works, so I would think so. Do I believe that if we overcome decoherence that faster than light communications will be achieved? Well, actually, technically, quantum entanglement is faster than light. It's happening now. So we've got that. Someone did ask me a question I put off till I get the others. Why would I go and get additional doctorates? It kind of became a hobby. I'm not any good at golf, so I go to school. I just keep going to school, although that's going to come to an end soon because I'm discovering newer universities look at my background and go, why in the heck do you want to get a degree? No, I've been told no twice to another degree this year, so this hobby may be coming to an end. I think we've gotten through all the questions. If I missed any, you should feel free to email me. Now, I cannot promise I'll email you back right away, but I can promise I will email you. And I just put my email out there. Thank you very much. I hope this was worth your time. I hope you come away knowing something more than you did before we started.
All right, thank you very much, Chuck. Again, this is Bob Burke with Region 4. We do appreciate everybody attending tonight. We had a really great turnout. We had close to 300 people. And so that was one of our best turnouts ever. So Chuck, thank you very much. It was a great talk. And for the folks out there who might want to have other topics, please send them along to me. We're looking for topics and speakers. So if you have any ideas that you'd like to present, please send them over and we'll try and arrange things. And then, as I said at the beginning, if you need a PDH certificate, the easiest thing to do is to send me an email. One came from my personal account, an email to you, so you can just respond to that, and then I'll send it to you without spamming everybody. So if you need one, I can send it out. Again, thank you very much, everybody. Thank you very much. We will end the presentation now. Good night.